here's a time lapse of the melting and freezing experiment. We go through it and we can see that we're warming up a sample of an unknown substance in a hot plate. It melts at one point. We continue to heat it. We swap it over then and we let it cool. And it eventually will start to refreeze here, and we watch it go through the freezing process. And we're collecting data in both the water and the test tube throughout the process. So let's go back through it again and break it down a little bit, and then we'll do it a little bit more after that. So we're heating up the substances. The water and the substance heat up pretty much together. We can see the graphs look very similar. Some subtle differences, but about the same. And then we reach a point where the graph of the unknown takes a turn and it starts to melt. It stays fairly flat throughout the melting process until the substance is completely melted inside the test tube. We have a little situation where there was a chunk of solid that fell off the test tube and created a little hiccup in the graph. But eventually we got it fully melted, transferred it over then off the hot plate to let it cool. And the substance cools off until eventually we reach a point where we notice some crystals start to form. And once again, the temperature graph plateaus in the unknown while the water continues to cool. It sits there until it reaches the fully frozen condition. And once it has reached the fully frozen condition, the two temperatures both begin to fall. Again, the unknown kind of catches up with the water, and by the time we finish the experiment, both the substances are at the same place. If we take a closer look at the graphs, you can see both substances, we essentially start out at room temperature, pretty close to it, in the low 20s. And then we go through a period where we're heating the substances. So we heat them, we heat them up. We had a state change. We have this little blip from when the piece of solid that was stuck to the side of the test tube fell down onto the thermometer. So we see the temperature drop momentarily down to the melting point, but then as soon as it goes away, it resumes heating again. Then we take everything off of the hot plate and things begin to cool, and the water just kind of goes ahead and cools because it doesn't undergo a state change. But the substance that was in the test tube, the temperature stops changing again, the curve flattens out, and then that is when we observe it going back into the solid state. So if I kind of take and simplify the graph a bit, we have this segment, and this segment, and this segment. So really these are the different components of the graph. So we have a period of time where we are increasing temperature. So that is when the hot plate is transferring heat to the water and then the water to the test tube. And you can see evidence of that happening if we look at a certain point like here where the water is just about at 70 degrees Celsius. And if we come down on the graph to the same point on the unknown, and it's just a little bit lower than that, signifying that the test tube is lagging just a little bit behind the water in terms of temperature. But that's all thermodynamics stuff. So the motion of the particles is increasing, but we get to a point right here where the particles cannot speed up anymore and be in the solid state. So as we continue to pump energy into it through the water from the hot plate, the water keeps right on going because it's not undergoing a state change, but the substance, the particles stop speeding up. They cannot increase their speed anymore, and so they have to undergo a state change. So this is the point where the substance begins to absorb the enthalpy of fusion, and so the energy is still going into the substance, but instead of the particles speeding up, they're undergoing a restructuring. Their attractions are moving apart, and the particle relationships are becoming more flexible. It becomes more fluid. It becomes a liquid. And once that happens, once that's done, then the particles in their new liquid structure can begin increasing their speed again, and that heats up until we reach a point where the water is actually undergoing a state change. So this number should be familiar to us. roughly 100 degrees is the boiling point of water. So we see the water's temperature plateau as it begins to change state, and that means that's as hot as the unknown in the test tube can get, because the water, the liquid water that it's submerged in, is not going to get any hotter than that. Then as we take it off the hot plate, we start to decrease. So we're increasing temperature here, we're decreasing temperature here, so the particles slow down until they reach a point where they can't slow down anymore in the liquid state. So the substance has to release the enthalpy of fusion. It undergoes the freezing process. As soon as it's fully frozen, then the particles begin to slow down again. And notice that at the end of the process, this substance is right at about 80 degrees Celsius here. If we come up and we check out water at that same point in time, the water, where did my thing go? The water is just right there, just under 70 degrees Celsius. So there's a more than 10 degree difference. And so you get this fairly steep slope as the unknown in the test tube essentially catches up to the water, and we look at the very end of our test here at these two numbers. The substance is right at about 60 degrees, and the water is right at about 60 degrees. They've come to equilibrium with each other, and presumably they would continue to cool off slowly over time until they reached room temperature. This is a very good example of a temperature curve reflecting change in state, reflecting the idea that enthalpy, the energy of the structure, is different from temperature, and that there's sort of this idea that a substance must gain or release a certain amount of energy above and beyond the temperature that's needed for the substance to start undergoing that process. So for this substance, the melting and freezing point, the melting point and freezing point is around 80 degrees Celsius. It's very important to notice that these two processes ended up being at the same point. They're the same thing, and that's another important idea, is that melting and freezing are really the same processes, just happening in opposite direction. The same thing holds true for boiling and condensation as well, which would be what water was doing up here.